Hello and welcome back to Ordinary Differential Equations, the video series where we talk about solutions for such equations given by derivatives. And in today's part 9, we will talk about the uniqueness of solutions of a given initial value problem. And the key ingredient for that will be the so-called Lipschitz continuity. More precisely, here we will talk about locally Lipschitz continuous functions. However, you already know, before we start, first I want to thank all the nice supporters on Steady, here on YouTube or on Patreon. You make it possible that I can create such maths videos here. Okay, then let's start with the topic of today, which is about Lipschitz continuous functions. And in order to get the idea, let's start with an ordinary function from R into R. And now you should already know from real analysis that we have two important properties for such a function. Namely, we have the continuity on the one hand and the differentiability on the other hand. Or even a stronger property would be that f is continuously differentiable. But either way, we know that differentiability implies continuity. And now I can already tell you that the Lipschitz continuity is the middle ground between these two notions here. So f being Lipschitz continuous is more than just f being continuous, but still less than saying that f is continuously differentiable. Or more concretely, the notion we will now define is saying that f is a locally Lipschitz continuous function. Therefore, at this point, you should immediately remember that for these three definitions, for these three properties, we have these implications. And now it turns out that this new middle ground is exactly what we need, what we want to solve ordinary differential equations in a unique way. Hence, I would say, let's go to the definition of this Lipschitz continuity. Okay, so here we have the formal definition now. And let's formulate it with the notations we already used in ODEs. This means we consider a map V from Rn into Rn again. And you already know, sometimes the domain of definition is smaller than the whole Rn, and then we just choose an open set U. However, that does not change the definition at all, so we keep it simple here with the domain chosen as Rn. And now the function V is called locally Lipschitz continuous if it fulfills a local condition at each point in the domain. Hence, we would write the quantifier for all x in the domain, something has to be fulfilled. And here you see I want to use a compact notation, so I use the quantifier and the variable below. And as always in such formulations, we have the for all quantifier and the there exists quantifier. Okay, and now you might already know, a local condition means that we find that there exists a local neighborhood of this point x. And since we live in Rn, we can always choose an epsilon ball. Hence, for each point x, we find an epsilon greater than 0, such that the whole epsilon ball around x still lies in the domain. However, the domain was not the crucial part here, so let's immediately go to the point we actually want to discuss. Namely, we want to discuss the difference between two values of v. So let's write v of y minus v of z. And this difference we just measure in the standard norm of Rn. And now Lipschitz continuity always means that we have an estimate for this distance. More precisely, you should see here on the left hand side we have a distance for the outputs, and now we want an estimate with respect to the distance of the inputs. In other words, on the right we now have y minus z. And of course also measured with respect to the standard norm in Rn. However, now the concept of Lipschitz continuity allows that there is a constant L included. Moreover, the crucial point here is that this capital L works for all y and z simultaneously. So in other words, we write there exists such an L greater than 0 such that for all y and z the following property holds. And now the thing that makes this local is that we only need that inside our epsilon ball. Therefore you can simply remember we find an epsilon ball and a constant L such that we have this estimate for all y and z inside the epsilon ball. And then usually this L we can simply call the Lipschitz constant. Okay, with that now you know what it means if we call a function v locally Lipschitz continuous. And now from this definition we can immediately conclude two important things you definitely should remember. Indeed, we have already discussed that in the beginning of the video, but now we can actually prove this fact. First, if you have a locally Lipschitz continuous function, it's definitely also an ordinary continuous function. In fact, this is easy to prove. Just assume you have a sequence of inputs and maybe we call them yn. And now if this sequence yn converges to another point y, we want to show that the images also converge. There, please recall, this is exactly the definition of continuity. However, here we already know we can measure the distance of the images by using the distance of the inputs. And now since the right hand side here goes to 0 when n goes to infinity, also the left hand side has to go to 0. In other words, we have the convergence of the images as well. And this immediately proves the continuity at each point in the domain. Okay, then in the next step, let's talk about the connection to the differentiability of a function. Again, let's assume we have a locally Lipschitz continuous function, which means we can use this estimate here. And now you can say, it's not a problem at all, let's bring the distance of the input space to the left hand side as well. Of course, for distinct points y and z, this is always possible. Hence, what we see is that this difference quotient here on the left hand side is now less or equal than our constant L. However, please don't forget, the constant L is the same for all points y and z in the neighborhood. Hence, we conclude that the local slopes we can calculate with this difference quotient here are all bounded by the constant L. So this means, locally, the slopes of the function cannot go to infinity. Indeed, this is a very important property of the Lipschitz continuity we will use in our ODE course here. However, before we apply these notions to differential equations, let's first look at differentiable functions. More precisely, I want to take a C1 function, so a continuously differentiable function. And moreover, to keep it simple, let's use the one-dimensional case here. In fact, that is also the reason I call the function f instead of v again. Okay, now let's fix a point x and an epsilon neighborhood around it. And then we know we can just look at the secant slope from before. However, now in the one-dimensional case, which means the norm is simply the absolute value. And now you might already recognize for a differentiable function here, we can use the mean value theorem. This one implies that the secant slope here on the left hand side can be written as a tangent slope. In other words, we can use the derivative of f. The only thing we need here is an intermediate point we can call xi. And you know it's an intermediate point, so it lies between y and z. So if you're not familiar with the mean value theorem, you should watch my real analysis course again. Okay, but here we have to add something, because we have the absolute value on the left hand side, we also need it on the right hand side. And indeed, this makes it better, because now we can estimate the right hand side as well. For example, we could say we go through all possibilities this intermediate point could have. Therefore, let's call the new variable xi tilde and let's go through all the points in our epsilon neighborhood. Hence, we know we will definitely hit the correct xi on the way. However, now this supremum here, which exists, we can just call capital L. Moreover, at this point, please note f prime is by assumption a continuous function, and therefore this supremum here is definitely a finite number. In other words, this is a well-defined non-negative real number now. Hence, with that, we have the Lipschitz constant we need for the definition. Moreover, here I should tell you, it was not written in the definition above, but of course, the constant could also be just 0. It does not change anything, because you can always take a bigger constant if you already have one, but of course, equal to 0 would be the simplest case. Nevertheless, the conclusion here is definitely that our C1 function f is also locally Lipschitz continuous. Therefore, with that proof, you already know a lot of examples for locally Lipschitz continuous functions. Indeed, this is very helpful because this is what we can use in our discussion about ordinary differential equations. And here please note, this whole proof here in point 3 also works similarly in higher dimensions. And in the next video, we can use that and prove that for initial value problems where the function v is locally Lipschitz continuous, we have indeed a uniqueness of the solutions. So I would say, let's meet there and see you soon. Bye bye.